magnetic circuits, the way they work is your assumption is all the energy is inside the bar. Right? A magnetic circuit has a closed loop to a magnetic flux flow.
Yep.
You don't have anything that's external.
Okay.
So everything's inside. All right, anyway, I want to talk about boundary conditions, and I want to talk about lifting force of bar magnets. Some of this is kind of interesting to, I think, you've seen these electromagnets that lift up like junk cars and stuff like this. You're familiar with electromagnets?
Yes.
Right? I mean, there's actually magnets that are permanent magnets. That's where they polarize the actual magnetic dipoles and get that. Then there are things that are electromagnets where you drive a current through there and you create a magnetic field that effectively causes a lifting force to occur. Now, first, boundary conditions. Boundary conditions, let me start by saying when you talk about boundary conditions, the first thing you think about is, well, we've done boundary conditions before. When we talked about electrostatics, if you had region 1 and region 2, you found two things to be true. You found E tan in region 1 had to be equal to E tan in region 2. What that means is the electric field itself may have a vertical and a horizontal component, but at the interface, just above the interface, the tangent electric field, the electric field parallel to the boundary, has to be equal on either side of the boundary. That was the first. The second thing you notice is that D normal in region 1 was equal to D normal in region 2 if the surface charge density was 0. Do y'all remember that? Remember how, by the way, I'm going to ask the classes. A lot of times when you're going through this stuff, you don't really care how the proof works. You just care about the end result. Remember how we proved this, anybody? Anybody at all? How did we prove that? Well, this is electrostatics, so what's the integral of E dot dl around a closed loop? Just starting point, integrate the E field, think about gravity and work. If you move something in any path and bring it back to where it started, what's the net work done? 0, right? What's the net? This would be the voltage between what? Between A and A. What's the voltage difference if you overlap leads on a meter? 0. All right, what they do is, for this part, they simply go ahead and build this little imaginary surface like this, and they say if I integrate the E field on either side of the surface around a closed loop and let this difference, the height difference, go to 0, you'll get 0. That's how I did it. Do you remember this now? Anybody? Remember? If it wasn't 0, then you get a net voltage, right? If you integrate around here, it doesn't matter the direction, it has to be 0. Because you're measuring the voltage at that point to that point. It has to be 0. That's why E tan 1 is E tan 2. Okay? Now, what about D normal 1 equals D normal 2? Do you remember how we proved that? Assuming the charge density is 0.
Isn't it because E and D are related by...
Well, here's the two laws. You all remember this one. This is for electrostatics. The integral of E dot dl over any closed loop is 0. Now, what do you know about the integral of D dot ds over any closed surface? Say it.
Is it Q enclosed?
It's Q enclosed, right? If there's no surface charge, think about this. They usually build these little pill boxes that I'm not a real fan of. But they're saying we're going to have a pill box here. It's got a surface area A. Right? If you think about that, there's a D field, there's a D field, right? Now, if you say the net surface charge density is 0, then the integral of this D field in the positive direction, D magnitude times A, minus this, minus D, because it's pointing up, times A, has to be 0, or D upper, D normal upper, has to be equal to D lower. Do y'all follow me on that, class? How many do? That's all. Now, there is one different stipulation. What happens if there's a net charge density on the surface? If there is a surface charge density, something happened. Now you can tell, we could do it with an integral form. You can say if there's a charge density of rho s here, then the integral of d dot ds is no longer 0 over those two surfaces. It has to be the surface charge density times area. You remember that? Well, that was the case. Then you ended up, Whitworth does this. If you have a surface charge density, this is region 1, this is region 2, and the way he does it, he calls a unit vector, he calls this A21. I call it A normal, but it's pointing towards region 1 here. What they say is D normal in region, or D in region 1. It becomes a normal component. Mine is D in region 2. When you take that and dot it with the normal vector, or A21, you get the surface charge density. Do you remember this? How many remember something like that? No?
No.
Do you remember? Okay. Now, that's for electrostatics, right? I'm trying to draw the parallels. You'll see it. What about magnetostatics? Now you come over here and take a look at this. For magnetostatics, here's region 1, here's region 2. If you can tell me where this is in the book, I'd appreciate it. So it's boundary conditions for magnetic circuits. Anybody? You got a book?
I think it's 257.
Page 257? There, you're looking at it right there. Is that 257? Page 257. Okay, ready? Now, if you look at this, here we're going to do something, and I'm going to ask you what happens. So, if I take a surface here, like that pillbox from before, I'm trying to show you exactly the way I want to show it to you. Right? You look at this, right here, it's got a height h, area A. You can say there's a B field here and a B field here, right? Call it B normal in region 1, B normal in region 2. All right. Now, we're going to take the limit as h here goes to 0 of the integral of B dot ds over the closed surface. By the way, what is the integral of B dot ds over any closed surface? There's a fundamental reason I'm asking. 0. Why is it 0? You're absolutely right. There's no magnetic charge. Okay? It would be divergence of B over this. Divergence of B is 0. This is 0. Now just look at this. If you take B dot ds here, it has to be the same magnitude, opposite direction of B dot ds there. Therefore, B normal 1, and this is always true, B normal 1 is equal to B normal 2. That's always the case. Doesn't matter which side of it. The normal component of the B field is always the same. However, the tangent component of the H field will be equal to surface charge density. It will have a function of surface charge density. Usually H tan 1 is H tan 2 if there is no current on that surface. No surface current. You go with me? It's similar, but opposite in terms of the... Before, we know that E tan 1 is E tan 2. Over there, it won't be for magnetics. It's H tan 1 will equal H tan 2 if there's no surface current, but if there is, we have to do something else. But over here, D normal 1 was D normal 2. If there was no charge density, over there, it doesn't matter. There can't be magnetic charge. B normal 1 is B normal 2. Just remember that one. Okay, so now, onward and upward with with H. So, if I take a look at the two regions here, here's region 1, here's region 2, and now assume that there's a surface current. Please just watch it. So assume you got a surface current. And that's going to, the surface current is a vector, they use K. K would be in amps per meter, it's got a vector direction. You go with me? All right, now I take a loop. I'm going to take this loop right here. I'm going to let that be H, center this thing, and this is going to have a length L. And then I'm going to say, well, the current's coming out. If I go around this closed loop here, I get the integral of H dot dl, and I'm going to go in the counterclockwise direction. That will be equal to the integral of K here dot d length over the length. Now what I'm doing is, this is like using Ampere's law. If I go right around here, I need to do one other thing, the limit as H goes to 0. What you're going to see is something very obvious. You're going to see this thing is going to be H on that side, H on this side around the closed loop, has to be the current that's penetrating it. Does that make sense? Everybody. Follow me on that? All right, so if, in fact, the current density is 0, and I'm going to state this explicitly right here, so if, and only if, the surface current density is 0, then H10 in region 1 is H10 in region 2. That's 99% of the time. However, if it's not 0, now just think about this. Logically, you know if it's not 0. By the way, what that means is if you don't have any surface current, right? Then the tangent field below is the same thing as the tangent field above. That's all it means. You all with me on this? H10, that's all it means. But if you've got a surface current, something changes. Now, that surface current is going to cause an effect where it's going to increase the field on one side and decrease it on the other because of the fact you could just do this. Here's what you can do if you really wonder how you do it. H10 is H10 right? So if you have that you want something, you want to find out the surface current density, or the H field if there's a surface current density. First, don't have a surface current density. You're going to find an H field on either side that's the same. You with me? Then put the surface current in there. Now the surface current is going to cause, if it's coming out of the board, a flux to flow that way, above it, and the opposite way below it, right? Just add that flux to what existed already, and you've got the total flux. You with me? All right. Now, here's the way you do it mathematically, like over here when you had charge density. By the way, if you can give me the page number, this is on the book, I'd appreciate it. So, if you have two regions, call it region 1, region 2, and there's a surface current, call it K here. Then you can say that H1 minus H2, right here, I think he does it with A crossed, he uses the normal component, A normal, which is A21 here. A21 cross that will be equal to the surface current density. You got your book open, not
Yeah, it's 259. Yes.
I don't know which one there's a couple ways to do it. Yeah, he's going to use that form. H1 minus H2 is K. Now the reason he does this, and you don't have to do it this way, but here's really what this is doing. When you do the cross product right here, remember H has a normal and a tangent component. Y'all follow me? This cross product simply pulls off right here the component in direction of K, because the normal component is actually going to have, there's going to be a normal component of H possibly and a tangent, but a cross product of two things in the same direction is 0. So this gets the tangent component of the H field minus the tangent component on the other side is going to be Ks. That will always work. Y'all with me? We can do a few problems. All right, now, that said, isn't that almost the same thing you did for the boundary conditions with electric field and D field, right? At a region interface? It really boils down to simple math where you find you've got values on one side, you need values on the other. You simply go through them, find out what you don't know and turn the crank. It's really like the curls almost, where it's just a mathematical, you might say, turn the crank kind of problem. I feel like I should do at least one of these problems. Did you have one in mind? You were looking in your book for something.
No, I'm good. I can look for one if you want.
Sure, pick one and we'll do it.
Boundary conditions.
Is there any chance of rain today?
I don't think so, but I'm not sure.
I know I asked that a lot, but when I'm down here and I'm not looking at the weather, there's no windows, I don't have any clue.
6 to 10:30.
Oh, in the evening? That's fine with me. I don't mind the evening. All right. So, let's pick one. You got one for me?
I'm trying to read these. I didn't look at these before.
It doesn't matter. You can pick any. How about?
We can do 451.
All right. 451. What does this say?
Yeah. It says above the XY plane, z greater than 0, there exists a magnetic material with a mu relative.
All right. So this is what plane is this?
It's on the XY plane.
This is Z, so this is going to be X, Y, and up here, you got above it?
Yeah, it says above it, there's a mu relative of equal to 4.
Below it?
Below the, hold up. I don't think it gives below. It says below the plane is free space.
Okay.
And the field
Mu relative is
H1,
1.
it says and the field H1 equals 3AZ
Is
plus,
this region 1?
I'm not sure.
Yes.
Yes, I think so.
It is? Everybody follow me? Okay, so, go ahead.
Okay. Mu relative is 4. H1 equals 3AZ plus 4, or 3AX plus 4AZ.
H1 is 3AX plus 4AZ, go ahead.
Yeah. It said below is free space. It says find H2 assuming the boundary is free of surface current.
All right, so they want H in region 2 here, okay? Y'all with me? Now this is a classic problem. I want you to just take a minute and try to make sure you appreciate what we're about to do. Okay? Are you with me? Now, I want you to think about this. We're going to go through the rules and figure out what the H field is in region 2 by simple deduction. First thing I'm going to do is say H tangent in region 1 has to be H tangent in region 2. Do you all agree with that? That's explicit. Okay. There's no, it doesn't matter if there's a surface current or not. So what is the tangent H field? If that is 3AX plus 4AZ, there would be something that's going to have 3AX and it's going to have a vertical component of 4AZ. Do you all agree with that? That would be the H field, right? This would be HZ, and this would be HX. Do you all agree? Which one's tangent? I ask this, and I don't mean to be trying to insult your intelligence.
It would be HX.
Right. Tangent means it's going to be planar in the plane of the surface. So look where the surface is. It's in the XY plane at Z equals 0. What's in that surface? It's only X, right? If there was a Y component, it'd be Y2. Do you all agree with this? So here, I can say that H2's X component is going to be the same thing in H1, which is going to be 3AX. Do you all follow?
Yep.
Yeah.
All right, now, the next thing, since he said that the surface current is 0, is B normal 1, is B normal 2. Just hang on for 1 second. Is B normal in region 2, correct, class? We don't have B, we have H, don't we? What is H normal in region 1? Normal means perpendicular to the plane of separation.
The 4AZ.
It's 4AZ, right? All right, so we know H normal in region 1 is 4AZ. So what is B normal in region 1, class?
Mu 4AZ.
Mu naught times mu relative times this. So we know it's going to be mu naught times mu relative, which is 4, right? Is it in the top? Yeah. Times the actual H field. Mu H is B. And the H field is 4 as well. Now what does that equal? That equals the B field normal in region 2, right? We're going to get the H field component, but I can just say that this is equal to B normal in region 2. Do you all agree with that? All right. Now, everybody with me on this? What is B normal in region 2? That's equal to mu 0 times what's mu relative in region 2?
It's just 1.
1, right?
1. Yes.
Correct. In region 2. Everybody with me? And it's times H normal in region 2. So what is H in region 2? H normal in region 2? It's what?
16 AZ.
It's going to be 16, right? 16 amps per meter, and it would be in the AZ direction. So in H2, it's going to be plus 16 AZ amps per meter. Does he have the H field or B field? What does he have? What does he ask for?
He asks for, I'm not sure, where is it? Yes. It says find H2.
Okay.
So he wants
Find
H2.
the angle between H2 and the.
All right, we'll get that in a second. First, does he give you H2 in a vector form like that? or not?
No, that is, we
Yeah,
just
that's
solved
right
for
now.
it. It's right there.
RH2 is what he
Huh?
does.
It's right there, we just got it.
What?
That one right there. That's
I mean, but does he give it, he asked for it?
He does not give H2. He asks for H2, then he asks for the angle.
All right, is that H2?
Yes.
Okay, that's all. Now, he wants the angle between what?
That and the surface.
The normal or parallel?
what angle does H2 make with a normal to the surface?
Normal to the surface. So what he wants is this. All right, I'm going to try to draw here so you see. I'm just going up the z-axis. So we have H2, right? And H2 is 3 plus 16 AZ. So think of it this way. It's, no, that's about right. Sorry about that. It's going to have a value of, in the x direction it's 3, and the z direction is 16. So here is 16, and this would be equal to 3 when we need, he wants it with the normal. And here's where it gets a little ambiguous. All right. When you take a look at this, the normal's in this direction. Extend this line, and I want to make sure you see this. Y'all follow? Here's the normal, and here's the actual vector. I just extended through the origin of 16 and 3. In other words, the straight line. This is technically the angle, isn't it, class? This is the angle, right?
Yes.
So that angle is the inverse tan of 3 over 16 degrees. Do you agree with that?
Yes.
So if they did it right, this angle he wants of, I'll call it just theta, is going to be equal to tan minus 1 of, and this is going to be opposite 3 over 16. What is that? Anybody? What are you doing in degrees? Because I can do it.
10.6 degrees.
Say again?
10.6 degrees. Oh, I got that as well.
Now y'all follow me on that?
You said 10.
Huh? 10.6 degrees?
Yes.
Sorry. I guess my ears don't work. So 10.6, I'm sorry about that. So 10.6 degrees. Okay. What's the next part?
It's the same, but instead now K is
Okay.
5AX.
All right.
Yes, this case 5 amps.
5 amps per meter.
Yep.
Yeah.
We're going to do it here. So now this is part 2, or B, and the surface current is 5 amps per meter. In what direction? In Y or AX?
X.
AX?
Yes.
Yep.
Yeah, AX.
All right. Now, bear with me. All right. First thing I told you is that B normal 1 will always be B normal 2. Doesn't matter about the surface current. Y'all with me? So we know that B normal, and actually H normal in region 2. So H normal in region 2 was what? In the Z direction 16, was it? So it's just 16 AZ amps per meter. Now we're going to get the tangent component in the plane, XY plane. Y'all with me? So I know what I'm going to do is say the surface current density K is equal to A21 crossed into, and the way he has it is going to be H1 minus H2, I believe, in the way he does it in the book. Take a look at that for a second.
Yeah.
He has H1 minus H2. Y'all with me, class?
Yes.
But I'm going to show you something. So when I look at this, I've got to get A21. Be with me here, and I'm going to slow down. What is A21? It's a vector pointing from region 2 to region 1, according to him. I don't like this. I usually call it A normal. But A21 here is going to be what?
AZ.
Simply AZ. Got that right. So surface current vector here is 5A AX. Or 5AX. Just leave this there. That's equal to A21, which is going to be AZ crossed into, and here, just going to make sure you see this. I've got the H field in region 1, correct? The H field in region 1 is given as 3AX plus 4AZ. So let me just write this. So it's 3AX plus 4AZ. And it's going to be that minus the unknown H field in the X direction in region 2. And I'm going to call it, I'll get out of your way in 1 second. So I'm just going to call this HX2 AX minus, and then it's going to be HZ was equal to 16 AZ. And it's this. Just take a look for a second what I've written. You're going to see there's one unknown after we do everything. Please make sure you watch this because people mess this up.
I have a question. How do we know there's not a Y component?
We're going to do a cross, right? This is the definition, is it? Oh, we could put
Yeah,
a
well,
Y
I'm
component.
saying H2 is H2, HX plus HY plus HZ, and HZ is minus 16. Or, no, it's 16, you just added an extra
Oh, I'm
minus.
sorry. Let me do it. I'm sorry. Let's do this. Let me do this. First, there's no Y component here. Give me that.
That is,
In region 1.
yes, there's no Y component.
So
Yes.
what I'll do is this. There's going to be minus, and this is going to be some unknown X. So I call that HX2 AX plus some unknown Y2 times AY. We're going to do the whole thing. Thank you for that. And then it's going to be plus, doesn't matter, some unknown Z in region.
We already have Z.
Huh?
It was 16.
Yeah, but that's for when it's 0.
That's
that'll
the
be
value in the zero. I'm going to show you you're right anyway. All right. The normal component will always be the same. That's going to be H2Z AZ. Now, you're absolutely right about this, and I'm so sorry I didn't include that. Are you all with me on this, guys? Now, the next thing I'm going to do is just do the cross product, and I want you to notice something. And I thank you for that warning. 8x, you were absolutely right. Now, here I'm going to do it. I get AZ crossed AX here, right? Y'all see this? AZ crossed AX is AY, so it's 3AY. Right. Then I got AZ crossed AZ is 0. Then I have AZ crossed AX is
It would be negative AX, so it'd be a
AZ crossed AX is going to be AY with a negative sign is minus
Negative
HX2 AY. Do you agree with that?
Mm-hmm.
Then we have AZ crossed AY is
Minus A.
AZ crossed AY with a minus sign is plus.
Oh, so it'd be plus.
Plus,
maybe.
plus.
Yeah.
Plus, right? Plus H2 or HY2 AX. I hope you appreciate this. Finally, AZ crossed AZ is
0.
Take a moment, make sure you see this. Okay. I don't know what he did in the book, but this is the easiest way to do it. So by looking at this, what do you know HX2 is?
Has to be 3.
Right. So HX2 is 3.
So it didn't change.
That's right. And what is HY2?
5.
5. Take a look at his answers. I don't know what he has.
And HZ2 would still be 16.
Normal component's always going to be the same on either side. I mean, the normal component of the B field, not the H field. Pardon. Whatever the B field normal was in region 1 or the H field in region 1 before is the same as after that current is there. You all with me?
Okay, so the normal component's always the same.
All B normal 1 is B normal 2. Now the H field normal 1 is not the H field normal 1. It's the B field.
Okay.
Yeah, is that the answer, by the way?
Yes.
Okay.
That ain't your answer.
I don't care. Y'all with me on this? Now, honestly, I'm going to level with you. All these props, either the angle, magnitude, or components, boil down to those 2 laws, and it's really straightforward. Just keep the books. Make sure you keep the books and I'm so glad you said that because you're absolutely right about that. That current gave you an effective additional component that we didn't have before, and that was the X component. Or I should say the Y component. I'm sorry about that. The Y component. I want to say one other thing too. I don't make a big deal about this, but I expect everybody to know that H tan 1 is H tan 2 anytime there's no surface current. However, and hear me now, when you have a perfect conductor, then the surface current density, K, will be the magnitude of the H field on the other side, because there's no H field below a perfect conductor.
Yeah.
That's important. And do you remember if you had a perfect conductor with a charge density rho s, the D field normal was just equal to rho s. Right? And I'll spend more time emphasizing that as we get through this, but this is real important to know. If you've got a perfect conductor as a surface, so, you know, then things change.
What about things that are insulators that can become a conductor?
You mean semiconductors?
Yeah, well, yeah.
Well, anytime you have the ability to have a field present, it's not zero, then you got to solve the entirety. You got to have H tan 1 is H tan 2. I mean, so B normal 1 is B normal 2, and H tan 1, A21 crossed into H1 minus H2 is surface current density. Then you have to do that if it's not a perfect conductor. All right, let's keep going. All right, so that's the tangent H field and B field business. Now, now we got to do forces. Now, you all know what electromagnets are, right? I mean, basically, if you run a current through something, it could be DC or AC, you're going to generate a magnetic flux. There's going to be a lifting force. I'm going to do the classic one. Where's this in your book? Look at the bar magnet business. It's going to have magnetic forces, but this time it's lifting powers towards the end of the chapter. When you talk about this is a fundamental physical principle. So if we have a bar, like so, he always shows you these things in a U, and I like that. A bar like so. Then you got a bar beneath it.
274.
And you got some little gap here. I'll call it L gap. Y'all with me? And then I'm going to quote, and this is one of those things that's going to have a cross-sectional area, A. It's going to have some permeability, mu, right here, mu. And usually mu is much greater than mu 0, almost always. Y'all with me? So what we're going to do is figure out if you have a bunch of coils of wire, and you have a current I in here and N turns. We're going to figure out the lifting power of this thing.
Okay, wait. So what's mu on top?
This is mu, it's just in the bar. It's a bar that basically is this kind of thing.
Yeah. Do they have the same what's it called?
T relative.
Okay.
And the only reason, it doesn't have to, but the reason I'm doing it is because it'll make my life and your life easier. For understanding the basics. You with me, class? All right. Now, if you look at this for a second, we're going to assume this gap 0. So I'm going to assume the gap LG is approaching 0. You with me? And what I'm going to do is take a look at this magnetic circuit. Now, this magnetic circuit can be drawn like this. Don't get too hung up about this. I'm trying to make it as easy as possible. I'm going to keep the cross sections of both of these the same. This indicates cross section. So A is the same here and here. U is the same. And we're going to do something here that's a little different. I'm going to say the total length of the upper one from center to center is going to be L. And from the lower one, I call it L1 and L2. Can you all follow me, class?
The whole thing is L.
L1 plus L2. Now, you start by assuming the gap doesn't exist. What you do is this. Draw the magnetic circuit, the equivalent magnetic circuit. It looks like something where you have a flux voltage or an MMF of N times I. Then you have a reluctance that has to do with the actual upper one, right? And that's going to be the length 1 over mu cross-sectional area A. Can you all follow me? I'm making it as simple as possible. You
Yeah.
can add complexity. Then you're going to have another thing here that's going to be equal to L2 over mu A. And you can see that they're in series, and it shouldn't be apparent to you. Everybody with me?
Yeah.
Now, if you take a look at this, I can get the magnetic flux flowing here, right? Magnetic flux is like current. 2 series resistors with a voltage. Tell me this is like a voltage. This is Ni over reluctance 1 plus reluctance 2. Can you all follow me in that?
Yep.
And if I want to, I can even break this down. It's Ni over reluctance 1 and reluctance 2 are really going to be equal to 1 over mu A, just L1 plus L2. I'm trying to make it as easy as possible, remember? You all agree with that? Factor out if you've got 1 over, or L1 over mu A and L2 over mu A, add them up, you get L1 plus L2 divided by mu A. Now you can see what happens here. Now I can say that this is equal to actually Ni over L1 plus L2, and it would be times mu A upstairs. Everybody agree with that?
Yep.
Next thing we're going to do is get the B field and the H field. First of all, how do you get the B field anywhere in that box? The B field, by the way, is flowing around this way, and you'll notice this B field is normal to this surface. Can you all see that right there?
Yeah.
It would be normal. So what is that B field?
It'd
Well,
be
it's the total flux, right? Divided by the area, right? You'll notice something happening. What do you notice? Areas cancel. So this, all of a sudden, is equal to Ni over L1 plus L2, and it's going to be times mu. That's the magnetic flux. Agreed?
Yep.
What about H? Now, H will be a function of the value of mu. Can you all follow me?
H will be?
Take a look. That's B. B is mu H, right? H, I'm sorry, people. H, I said it. H, B field is a function of mu
Yes.
right here. And you can see one thing, it's going to be much larger in the bar compared to a gap, once a gap occurs. You all follow me?
Yes.
H will not be a function of mu. I'm sorry I said it that way. Okay, I'm going to keep going on, but remember what I just said. Now, if you take a look at this, if you allow a very, very small gap, this is the way you think about this problem. Let this thing just separate by a nanometer, or 10 to the minus 21st meters. You all with me in that class? Now, there's a certain amount of energy here and energy here. Right? Now, energy density, you can write it many different ways, but technically it's 1/2 mu H squared in terms of a density of joules per meter cubed, right? Do y'all agree with that?
Yes.
Now I want you to just look at this. We could calculate the total energy in these two areas, and I'm just going to use a capital W. The magnetic energy in these two little gaps would be the volume of the gap, which is going to be L times the area times 2. And the reason it's times 2 is because there's 2 gaps for this electromagnetic to work. And we're assuming this length L is going to be, I can call it L gap. L gap is, and I'll do something like this, small, it's approaching 0, it's small. Now, if I take that and I multiply it by the energy density, which is going to be 1/2 mu magnitude of H squared, now I get the amount of energy in that gap. Can you all follow? This is the fictitious gap. It's very, very small, so it's insignificant change in the flux. Y'all with me, class?
Yes.
And as the gap gets bigger, the actual lifting power goes way down. You'll see this in a second. So next, after that, y'all with me on what I'm doing? Now, can you see the 2's cancel?
Yep.
So I'm going to take the 2's away. Now, what do I want? I want the lifting force. If you have energy in a system and you want to know the force that would be moving anything, you always take the derivative of energy in the system versus the dimensions it can actually move about. You all follow me? So if I take the derivative of the magnetic force with respect to Lg, or with respect to the length, what I end up getting is area times mu h squared. Can you all follow me? And that is actually the force. It's minus, he'll have minus F, but the sense of that is trivial. And here's the one thing I want you to take from that. The force that's going to be exerted on this will try to close the gap because it's a minimum energy principle. If you remember back in the days when you had physics, one of the things that they try to really beat you down with is that anytime you're wondering about what a system does, it goes to a minimum energy. If you have a ball that's got a certain potential energy and you have a ramp and it's affected by gravity, you always roll down the ramp to the bottom, all right, where the potential minimum energy is 0. You all with me? Well, the potential minimum energy in this thing is when the gap is closed, and this is the force of attraction. Now, has anybody ever used a permanent magnet to lift up things? How many of you have experience with electromagnets? Anybody? Usually it's DC current driving electromagnet. They're solenoids, for instance. And the lifting power on them, what you'll see is if you try to lift something up, it'll go very slowly if you took a high-speed movie camera, and then all of a sudden it goes fast. Because the closer it gets, the greater the force. All right? Now I'm not going to go ahead and write the definition of this. I'm talking about the lifting power when the gap goes to 0. That's what it is. Does he have that in the book?
Yes.
And that's the magnetic force, and it's tending to pull this bar up. Now here's a classic problem. I try to make this very simple. Now, how do you do a problem like this? First, you calculate the flux that would be present in the bar after you shut the gap. You all follow me? Then after that, after you have that, you calculate the H field in the gap. It's in the gap, by the way. It's not in the bar. You all follow me?
So it would not be what we calculated. It would not be a function of that B field.
It's this. You divide by mu, right?
Oh, so it is.
And you get 1. That's H, right? That's H in the gap. You all with me? Now, once you have that, you got to square that, right? And there is a mu, but this is mu in the gap. This is mu 0. All right? It's not mu relative times mu 0. You all with me? And
Why is that mu 0?
Because it's the energy in the gap. The gap is air. All right? Air has a mu relative of 1. You all with me?
Okay.
That's the only thing. So this is going to be mu 0. This will be the lifting, and he has this in the book, right? Now you can write in terms of the B field. Don't do that. Make sure you say H. If you do B field, some people always go B field in the bar. It's not that. It's always going to be the H field there squared times mu 0. With me?
Is it supposed to be negative?
It ain't going to matter. It's attracting. It's pulling up. I mean, if you're above it, the force on this is pulling down. If you're below it, the force on this section is pulling up. It's trying to close the gap. And but I hope you all understand this, right? So what happens if this has mg? If there's a force of gravity on this, and we want to know the minimum value of the current that could actually lift it, what do? We set this force, and then we put it in for h, that, right? Equal to mg, and we solve for I. Correct on this, class? Okay. I hope, do you all understand this? It's really that easy. There's nothing that, it's all it is.
Okay. Yes, that's good. Yeah, that works.
I mean, I could do it. I think you guys can handle it. There's an example in there, right?
Yep.
I want you to just take a look at the example. And by the way, anytime he'll have things where they want to know the force pulling two things together, assuming a certain gap, then you have to do the magnetic circuit with the gap present. Y'all hear me? And you got to figure that out. But in general, they always, with electromagnets, they want to know the lifting power. So they assume the magnet's going to slam down on something, and the gap will go to 0, and then you do that.
Could you use this for lightning?
No, this has nothing to do with lightning.
I didn't know if you could calculate the H field in the cloud. and the
You
ground.
can calculate the H field created by lightning. It's a time varying effect.
Well, I'm saying from the cloud and then one from the ground and then figure out the work that's being done in it. I didn't know if that was a thing.
I'm sorry, the cloud is a static charge, right? Lightning will draw a current, but the current goes right to Earth or it's inner cloud
Well, I'm
lightning.
talking about the droplets of rain and the ice cubes falling down and creating.
Sue me an after.
Okay.
Right? Because, anyway, this is kind of wild. But now this is just the lifting force and stuff like this, but magnetic circuits, and you know what a solenoid is?
Yes.
You energize it, it shuts the thing. It basically has a spring separating two pieces of metal. You energize it, shuts. It's a switch, that's all it is. You release the current, open. So it's a switch that can have a huge amount of standoff voltage difference, or it could be something like a plunger that's actuating something that needs to be hit or pushed. And it's a magnetic force, but they don't have coils of wire. Anyway, that's magnetic forces, and that's it for chapter 4. Now, I'm going to give you problems. Don't worry. Related to this stuff, please send me an email. Dr. Dubinsky, make sure you post the problems. I don't want you to get behind in this one. This is important you keep up on Monday. Because come Monday, now we're into stuff that gets a little hairy, the time varying fields, and that's the first part. I mean, the last part of the lecture I'm going to do. I'm going to take 4 or 5 minutes to do this. The quiz problem is easy, right? I want you to pay attention to this. Now we're in chapter 5, and I'm just going to tell you the bottom line of this. So there are 2 or 3 people in the history of electromagnetics that made tremendous contributions. One is Ampere. You know Ampere's law? We talk about it. The other is Gauss. You know Gauss's law. Both physicists back somewhere around 1650 to about 1750 in that area. They're old. I mean, that's ancient. Think about going way back to Bach and stuff like that at that time. Now, then a guy named Michael Faraday. Actually, let me go into it. So James Clerk Maxwell is the guy that really took all this stuff. Faraday's law of induction was observed. Ampere's law, Gauss's law, all this stuff led up to what James Clerk Maxwell put together. And he actually, from his equations, the speed of light was determined exactly, or it was at the precision of the actual prior experiments with magnetism and electrostatics. This is beautiful. I mean, obviously I like it, but this is really something. So here's the laws in a nutshell. Remember before you had curl of H was equal to J. Do you all remember that? That's the point form of Ampere's law, right? Normally it's integral of H dot dl over closed loop is the current penetrating, but this would be the differential. Well, based on something Michael Faraday saw, and here's Faraday's law in a nutshell, he saw curl of E, the point form of his law, is equal to minus dB dt. This is the point form of something that has to do with time varying effects, where the integral of E dot dl around a closed loop is actually, I'm not going to even go there right now because there are certain things that I can't explain in this time frame. This is the point form of something that actually Michael Faraday observed. This is Michael Faraday's law of induction. It's time varying now. And what that led to is there's a partial of D with respect to T in this law. No longer is curl of H just J. There is a partial D with respect to T, a time derivative of the D field. Now I want to say one other thing too. The way all these things were determined is experimentally. It wasn't like some great revelation from heaven. And they found out that this exactly fits. I mean, the mathematics exactly describe this phenomenon for all currents, all time varying, everything. All right, now that's the first law, and now this is called Ampere's law. That is true. The second law is this, Michael Faraday's law of induction. Whitmer's book's going to have a lot of things that are intermediate steps on this, but this is it. This is time-varying phenomenon. It accounts for everything. One thing you don't see here is anything with divergence of D or anything like that. Still Coulomb's law, things like that, and the point form of Gauss's law apply. There's still a divergence of D equal to rho V. That will always be the case. It doesn't change with this. This is always true. However, these two laws describe phenomena entirely. Now, I want you to write down the coupling effects. I call them coupling, the relationships between J, D, H, and B. You know that B is equal to mu H, right? We just did this. We know that D is equal to epsilon E. And we know J is equal to sigma E. Y'all with me? Those are always, always, always true. And when you get down to the quantum level, we're talking about individual photons and stuff, then some of the stuff becomes a little more statistical, but I'm not going to go there now. But generally, and almost, actually, even at the quantum level, this stuff works. But then you get into discrete values of possibilities. So you get this. Now, next thing after that, you come over here, and here's what's usually done. Now, you know you can solve equations in the time domain. If you have derivatives like this, we're going to get forms of equation that are integral differential equations. However, if you make the assumption that you're in the frequency domain, so now we're assuming we're at constant omega. Now, this is phase. Every time we have a time derivative with respect to t, that's equivalent to multiplying by j omega. Do y'all remember this? Right? Remember when you had L di dt for an inductor, right?
Yes.
The voltage here was equal to L di dt. Well, if it is if you're assuming a constant frequency, you get a phasor domain, it's just j omega L, right? The ddt becomes j omega. Do y'all remember that? Remember, for an inductor, the impedance was just j omega L. Does everybody follow me on this? Okay, so if we take these equations, what we're going to do is we're going to get two equations with just the E field and H field as variables. Then we're going to develop one equation. I'm just about out of time. So I'm going to tell you, in a nutshell, here's what happens. Look at the first equation. I'm going to ask you, do you see how it becomes curl of H is J? Well, J is sigma E plus the partial with respect to T of D. Well, D is epsilon E, so it's epsilon times the E dt, and the E dt just becomes J omega E. So I can write the first one, take my word for it, as sigma plus J omega epsilon E. Now, I've put the derivative substitution of J omega in there, and I've replaced D with epsilon E, and I've replaced J with sigma E. Y'all follow me? I'm going a little quick, I know. Everybody with me on this? Next one is going to be curl of H, or curl of B, pardon. Curl of B, sorry. So this is curl of E. Curl of E, curl of E is equal to minus dB dt. The time derivative becomes a j omega, that becomes minus j and then mu h. So these are the two equations in the phasor domain that have E and H only. I've put in the coupling coefficients in there. Can you all see this? Anybody got an idea? If I have this equation, I just want to see. Anybody have an idea? And I have this is equal to curl of H, right? See if anybody gets this. What if I wanted one equation with just one variable, say E? How would you get from those two? Your gut tells you if you got two equations and two unknowns, you should be able to solve for one equation, one unknown, right? Well, we can do it a couple ways. This is the easy one. What if I take another curl of this? Now I get curl of E is equal to minus J omega. We'll assume mu is not a function of position. Mu times curl of H, right? You agree with that? How many see where I'm going? What do you see up there? Curl of H is equal to
That and
yeah.
you substitute.
And here's the upshot is going to be minus J omega mu, And then over here, we're gonna have sigma plus j omega epsilon times E. And now I have one equation with one unknown. I have curl of E equals all that. On Monday, I'm gonna pick it up from there. I wanted to just throw that out there and allow you to think about it. And I'll admit, some of this gets hairy. So now, can you fill up the first row? You guys, you two can stay there, and we'll do them over there, and then the rest of you can stay right here. I just need to separate. Can you do me one favor? Either move to that desk or move in front. It doesn't matter where.
Yeah, I'll move.
All right. So do me one favor. Put your name on this list first.